Да, слышно? Проверка. Проверка. Слышно? Да. Ну и что? Все нормально? Okay, so yeah, hope that you received your information about homework grades. Yeah, so actually to those who got less than 10, I sent their homework with my remarks. To those who got 10, I didn't send homework, but you can see your grade on the web page. Okay, but first, yeah, actually, I would like to make some remarks about homework because actually not all of you solved it correctly. Yeah, so remark about homework 1. First of all, an important remark that there was a small incorrectness that in the formulation that the open subset of Riemann surface should be connected. Okay, so U should be connected. So it was forgotten. So I just it was the formulation was that for any open subset of X, the set of meromorphic functions on U is a field, but it is not correct. I mean, U should be connected. Why is that? Because otherwise it's not true. So otherwise consider, for example, I don't know, x is equal to c, and U is just the union of two disjoint subsets. Yeah. And U is just the union of two disjoint subsets. Yeah, and then you consider you can define. So and then here define F0, and here define F1. Yeah, then clearly 1 over F is not meromorphic. So so M of U is not a field if U is not connected. Okay, but one student noticed that. Okay, and then there were some just probably before I present a correct solution, I just want to make some comments about some common mistakes. Yeah, so several people said that that the number of poles is finite. So okay. Okay, maybe just again remarks. The set of poles is if F is a meromorphic function on U, then the set of poles is not necessarily finite. The set of poles of F is not necessarily finite. Yeah, several people from the very beginning assumed that it is finite, but I mean it's not correct. For example, you can consider, I don't know, u equals x equals c, yeah, and then f is equal to, I don't know, 1 over the sinus z. Yeah. Okay, you get a meromorphic function with an infinite number of poles, obviously. Okay, then yes, of course. Yes, and then also several people also said that f is the fraction, is the ratio of two holomorphic functions. But I mean, it's also not correct. So f, if f m of u, then f is not necessarily the ratio of two holomorphic functions. Is not necessarily the ratio of two holomorphic functions. Yeah, for example, u equals x is compact. If so, example, I write example. Yeah, here example. If u equals x and x is compact, then we know that there are the only holomorphic functions are constants. Yeah, but we can have many meromorphic functions. So, for example, I don't know, CP1. Then we have many meromorphic functions. On CP1. Actually, we know from the previous lecture that they can be described as the ratio of two polynomials. Many meromorphic functions, but holomorphic functions on CP1 are just constants. Yeah. Yeah. So obviously, any meromorphic function cannot be expressed as a ratio of two holomorphic. Yes. Also, there were some people who were saying something, trying to use some complicated material like Mittag-Leffler theorem. I mean, but it's actually much more complicated result, and actually even those people who tried to use this much more advanced technique did not apply it correctly. Here, maybe I just want to make one remark that some people tried to say, oh, consider zeros and poles of this function, and then they tried to find some other function with this the same or with the same poles. Okay. Maybe okay. Okay, maybe I just would like to make one remark that probably again you should be careful, because I think several people tried to use this fact that suppose f x is a Riemann surface. And suppose we have some points, you know, p1, p m, and q1, qn, some points. And suppose we assign some multiplicities to these points. Yeah. Then it is not true that if you assign some multiplicities here, then you can always find a meromorphic function with prescribed zeros and poles with prescribed multiplicities. So it is if you prescribe if you assign some multiplicities to these points pi and qj, then it is not true that you can all it is not always true that you can find that you can find f, some meromorphic function on x, having zeros at pi and poles at qj with prescribed multiplicities. Yeah. So if you fix some points and then you say, and assign some multiplicities to these points and to these points, and then you say, okay, and some people tried to say, oh, consider, some people tried to find some meromorphic function having prescribed multiplicities, having zeros at pi's with some prescribed multiplicities, and having poles at qj's also with some prescribed multiplicities. But I mean, it can easily happen that there is no such function. So also you should be careful here. Okay. Yeah. Then probably this is all about my remarks about your solutions. And actually, the correct solution is very simple. So in solution, so it is very simple. You just say that okay, so you have some poles, so okay, you have u in x, f is a meromorphic function on u, f is not equal to 0, yeah, and u is connected. Then so denote by p so the poles of f, by z zeros of f. Then 1 over f. 1 over f. We want to check that 1 over f is a meromorphic function, but okay, clearly 1 over f is a holomorphic function on u without zeros union with poles. Yes. Yes. Then yeah. So then first you should say that P is a discrete set. Yeah, we know that P is a discrete because it's a meromorphic function. Then also Z is discrete. So Z is a discrete set. Is a discrete. Because of the identity theorem. Because if this set has a limit point, then f should be identically 0. So Z is a discrete set. So it means that this set also consists of isolated points, so it's also discrete. Yeah. Then then if you consider now a point if you have some pole, then 1 over f goes to 0 when x goes to this point P. So then this implies that 1 over f is holomorphic at P. Yeah, so that 1 over f can be extended as a meromorphic function to the pole. And then you say that if you have a 0, then obviously 1 over f goes to infinity. The absolute value goes to infinity when our point goes to Z. Yeah, because yeah, f goes to 0, so this thing goes to infinity. Yeah. Okay, then we conclude that 1 over f is a meromorphic function. So is a meromorphic function with U. Yes, and the fact that it's connected is used here when we say that the set of zeros is discrete. Because we say that suppose it's not discrete, then by the identity theorem f is 0. But in the identity theorem we use that the set is connected. So actually the fact that it's connected is important. Okay, are there any questions? Okay, so now we go to the next topic. We will talk about sheaves. So probably during this lecture we even will not have many complex analysis because yeah, this we will study the general notion of sheaves, which is used in many subjects. Okay, so first we let us start with a definition of a pre-sheaf. Suppose X is a topological space. Topological space. And I is the system of open sets in X. Yeah, is the system of open sets in X. Yes. Then appreciate. Then appreciate. Appreciate of abelian groups. Abelian groups on X is a pair F rho where F is the family of abelian groups assigned to each open set in X, where oh, maybe better say consisting of a family F U of abelian groups so meaning that to each open set we assign some abelian group. And the second is the system of homomorphisms. So a family rho. So rho is a family of homomorphisms. Rho UV, where U and V are open sets and V is in U. Of group homomorphisms. Homomorphisms rho from F U to family of group homomorphisms. Yeah. So simply we have U, and then inside V, and then so this is a group homomorphism. Yeah. So which goes from F of U to F of V. And we require the following obvious properties with the following properties. That rho U so is equal to the identity map, identity F of U. Yeah, because rho U is a map from FU to FU. Yeah, we require that this is just the identity. And the second property says that if we have three open sets, U, VW. Then you can restrict from f of u to f of v, and then go from f of v to f of w, and then the composition is the same as going from fu to fw. That rho. So first we go from rho uv composition, rho vw should be equal to rho uw. Yeah, where we have w is inside v, inside u. Okay. So this is the definition. What are the examples? Okay, the main examples. The main example where one can immediately see that these properties are satisfied is the following. Yeah. First of all, some remarks about notation. Some remarks. The first one, of course, strictly speaking, a pre-sheaf is a pair, but yeah, this row is usually not written, so often write f, just f, instead of f row. Then the second, this row u are called restriction homomorphisms. Are called restriction homomorphisms. And then often we will often write f restricted to v instead of rho u v f for some element f in f of u. Yeah, so this will be the typical notation. Okay, and then of course here you see that the thing so the thing that we consider abelian groups is not important. We could consider sets or rings, and okay, so if we can consider pre-sheaves of sets, and then we just say that these restriction homomorphisms are just maps. Yeah. And if we consider the pre-sheaf of rings, then we require that these restriction homomorphisms are ring homomorphisms. So, of course, we can consider pre-sheafs of vector spaces. Yeah. So, analogously, can consider pre-sheafs of vector rings vector rings, sets, or vectors, sorry, vector spaces. Rings, sets, and probably some other objects. Okay, and then the main example is one of the main examples is the pre-sheaf of functions, in particular continuous functions. So, so examples. So consider a topological space. And then define C of U as the vector space of all continuous functions on U. The vector space of continuous functions with values with values in C. U in C. So U is open set in X. The vector space of continuous functions. Yes. And then and let rho U be the usual restriction of just the restriction of continuous functions. Just be the restriction of functions from U to V. So I mean, if you have a function on U, we can restrict it to V and get a function on V. Yes. Yeah, and then clearly this is a pre-sheaf. Yeah, clearly. C is a pre-sheaf. C rho is a pre-sheaf. Yeah, because yeah, and we have to check only two axioms. The first axiom is obvious. Yeah, you restrict a function from U to U. Yeah, and then this this is also obvious. Yeah, this condition. If you restrict from U to V and then from V to W, then it's the same as restricting from U to W. Yeah, is it clear? Yeah. Okay. 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 Probably an analogous thing but this can be will be useful. We can consider the following thing. So again, suppose X is a topological space. and G just some abelian group. Then we can define y of u is G if u is not empty, and 0 if u is empty. Yes. Yeah, and then and so and and rho u v of rho v is what? So I mean it's so what do we have? We have okay, we have several cases. So this is identity G if V is not empty, and zero homomorphism homomorphism if V is empty. Yeah, so if V is not empty, so U is also not empty, so both Y of U and Y of V is G, then we require that this guy is just the identity homomorphism, and yeah, and then if V is empty, then this is just zero homomorphism, sending Y of U to 0. Yeah, okay, and then again, one can easily see that it's pre-sheaf. One can actually interpret it as a sheaf of constant functions on sheaf of constant functions on X with values in G. As so pre-sheaf. Sorry. Yeah. By definition, I mean we define. What is your question? I mean we want to define a pre-sheaf. So for this we have to find these abelian groups for any open set and the restriction homomorphisms, and I would like to define them in this way. So Y rho is a pre-sheaf on X. It is called the pre-sheaf of constant functions on X with values in G. It is called the pre-sheaf of constant functions on X with values in G. Yeah, the first question is it clear that it's a pre-sheaf? Or you want to discuss that? Okay, yeah. So hope that it's clear. That's a pre-sheaf. And then yeah, it's called the pre-sheaf of constant functions on x with values in C in G, just because you can interpret it in this way, yeah, because you can here we considered the sheaf of continuous functions, the pre-sheaf of continuous functions, and here we can say that here we consider just constant functions, yeah, so meaning that yeah, we consider constant functions on open sets, yeah, with values in G. And then if you think in this way, then it's clear why this is pre-sheaf. Oh, I mean, it's then it's explains this definition. If you view this, yeah, as a pre-sheaf of constant functions. Okay. Okay. Here we yeah. So actually, you see, it's more or less the same. Yeah. Actually, 1, 2 are very, in some sense, very similar. So we consider some functions. But actually, yeah, actually, people consider more abstract objects. For example, the next example is the so-called skyscraper pre-sheaf. Again, some simple definition, but we will see that it will be used. This pre-sheaf will be used in our future lecture. So again, X is an arbitrary topological space, and yeah, we just fix some point in X, and then define C P of U as C if P is in U, and 0 if P is not in U. Yes, and rho U V. Again, it's yeah, it is just the identity map if P in V, and zero homomorphism if if P is not in V. Yes. Yeah. So yeah, we have, yeah, and this so, and then again, this is a pre-sheaf. Called the skyscraper pre-sheaf. Called the skyscraper pre-sheaf. Yes, I guess it's also easy. Yeah, that it's a pre-sheaf. Yes, and okay, and then actually and then actually one can have a completely abstract things, not necessarily connected with functions. So for example, okay, maybe this simple example. Suppose, so showing that actually, okay, so some other example. Suppose X is just 2 points with discrete topology. So suppose X is a topological space consisting with of 2 points with discrete topology. With discrete topology. Yeah, then we can define some pre-sheaf on it. So we have four open sets. Yeah, we have four. So four open sets, and yes, and then you can, for example, define for example, f x, f p1, f p2, for example, z. And f of the empty set is 0. And then and we can define restriction homomorphisms. Yeah, again, arbitrary. So and rho x restricted to p1 multiplication by some number multiplication by some a1 in the and yeah, and okay, pi, yeah. So restriction homomorphism from x to pi is multiplication by some number ai. Yeah. I equals 1 or 2. Yeah, and then and others are obvious. So and other rho uv are obvious. Yeah, multiplication by ai, and yeah, of course, obvious meaning that others are 0. Yeah, and then rho. Okay, others restriction homomorphisms are obvious. Meaning that, of course, there is a restriction homomorphism from X to empty set, but this is 0, and then, of course, so yeah, we have restriction homomorphisms from the set to itself, and then they should be identity. Okay, the only non-trivial ones are these two, and this is always a pre-sheaf. So then f rho is a pre-sheaf. Okay. Okay, some strange definition. I'm not sure that it's used anywhere. I just present it just not to show that this these rules are not very restrictive. You can create something by hand, and then actually I think that having this simple construction in mind is useful when you want to construct some counterexamples. In the seminar we will see some we'll discuss some problems. We will speak about sheaves where we will require more properties, and then I think that having this in mind is useful. For example, if you want to solve some problem like construct a pre-sheaf where some sheaf axiom is satisfied and other is not satisfied, so okay. Yeah. P1, но они же друг другу не вложены. У нас должно же быть одно вложено в другое, да? Вот, то есть, ну да, если вы подумаете, да, больше нет у вас нетривиальных как бы вложений. Okay. So yes, the pre-sheaf. Yes. Then okay. Then there is a definition of of sheaf. So definition. So a pre-sheaf is called a sheaf if two more properties are satisfied. So a pre-sheaf f on x, again the same assumptions, x arbitrary topological space. A pre-sheaf f on x is called a sheaf. It's called a sheaf if for every for every open set U in X and every family of open sets uj such that some family, so J is in J capital, such that U is the union U J. Yeah, the following conditions are satisfied such that and such that the following conditions are satisfied. Yeah, so if so the first one, if f, we have two elements in f of u satisfy f restricted to uj is equal to g restricted to uj for every j, then is equal to G. Yeah. Yeah, so we have our open set U, and it's covered by some other open sets. And yeah, this property says that if two elements F and G yeah, there are restrictions to any subset Uj. So if the restrictions to any subset Uj are equal, then the whole elements are equal. And then the second is the following. So given elements Fj in F of Uj such that, so if we have elements F of Uj for any j, such that Fj restricted to Uj Uk is equal to Fk restricted to Uj intersected with Uk for every jk in J, then then there exists F in F U such that F restricted to Uj is equal to Fj. Yes, elements of J such that given there exists F. Yeah, so what it says that okay, I draw. So we require that. So here we have element Fj, here Fk. And then we require that if we restrict them to the intersection, then the restrictions should be equal. And then this Fj and this Fk, they are restrictions of some element defined on the union. Yeah. I draw it for 2, but okay. Yeah, the condition is okay. The precise property is the following. Is this one? And these properties are called we will call them sheaf axioms. Yeah, I will following properties. We will call them sheaf axioms. Sheaf axioms. Okay. The definition probably at the beginning maybe not so clear, but let us now consider an example where these properties will be clear. First of all, again, some remarks. The first remark is that so this element f, of course, is uniquely defined by the first axiom. Yeah, so this element satisfies this property that restriction to uj is fj, but then by one it is defined uniquely. The element f from 2 is by the first property uniquely determined. Yes. Okay, maybe only one remark. The second I will probably give it later. Okay. Yes. Okay. Then what are the main examples? First of all, this pre-sheaf of continuous functions is actually a sheaf. C. So the pre-sheaf of continuous functions, the pre-sheaf C of continuous functions continuous functions on X is a sheaf. Yeah, indeed, the first property should be obvious. Yeah, so indeed. Sheaf axiom 1. Sheaf axiom 1 is obvious. Yeah, I mean, is it clear, the first one? Yeah, because if is it clear, the first one? Yeah, okay. And then, but yeah, the second is also, okay, so regarding, yeah, but yeah, okay, the second is also obvious, but okay, maybe it's boring, but still I present some arguments. So what about sheaf axioms? Sheaf axiom 2. Yeah, I mean, it's also very easy because what we have, okay, we have U is equal to the union J Uj, and then okay, you have Fj So C of uj. So you have continuous functions on these subsets. Yes, and then okay, and then okay, define f in C u as follows. Define f. How? You say that f of x is by definition f j of x, where j, where we choose an index j such that x is in uj. Yeah, I mean x is some element in u. Yeah. Okay, and then okay, since okay, if x is in some other k, uk, then of course f k of x is equal to f j of x, because by definition f j restricted to uj uk is equal to fk restricted. Yeah. Yeah. So this definition is definition is correct. So f is well defined. Well defined. So f, I mean f in cu. Yeah. So a function f from u to c is well defined. But then, I mean, you know that the fact that the function is continuous is a local property. Yeah, so it's standard fact that for a function to be continuous is a local property. For a function, for f, for a function to be continuous is a local property. So f restricted to uj is equal to fj is continuous. Implies that f is continuous. Yes. So yeah. So you see that this the second. So this is sheaf. So so this is a sheaf. Is a sheaf. A sheaf of continuous functions on X. Yes. So, yeah, is it clear? Yeah. Okay. So you see that yeah, these properties are obvious for functions. For functions, so yeah, so the moral is that yeah, more or less all sheaves defined with functions, all pre-sheaves defined with functions are usually sheaves, but you have to check that this property is local. Yeah, that we can consider some different types of functions, but the crucial fact is that yeah, the property that we consider should be local. Yeah, so here we use that yeah, the function that we consider, the type of function should be considered. Yeah, the defining property should be local. Okay, but okay. Anyway, yeah. The second example is this sheaf of constant functions, and it's not, of course, it's not in general a sheaf. So 2y is not in general a sheaf. Sheaf, for example, so for example, you take, I don't know, x is equal to r, and then you take what we want. The second property is not satisfied. For example, you take x is equal to r, and then you take u is equal to the union of two intervals, 0, 1, union, I don't know, 2, 3. Yeah, so you take two intervals, 1, 2, 3. Yes, and then you just and then you take g is equal to z. Yes, and then yeah, and then you say that the interval 0, 1 is u1, and this is u2. And then you choose f1 f1 is 0, and f2 this is in y of u1, and f2 1 in y of u2. So you define this element of our pre-sheaf as 0 here and as 1 here. Yeah, then there is no there is no f in y of u such that f restricted to u1 is equal to f1, and f restricted to u2 is f2. Yes. Yeah, because f this guy is just z. Yeah. So so when you restrict it to f is in y of u is just some number. Yeah, when you restrict it to this, you get this number, and to this you get this number. So this number should be equal, but you choose f1 and f2 to be not equal. So the sheaf axiom 2 is not satisfied. So sheaf axiom 2 is not satisfied. Yes. Is it clear? Yeah. Okay. Okay. Okay, and then probably for we have to finish soon, I guess. Yes. Probably I just introduce important pre-sheaves that will be used in the exercises. So yeah, analogously to to the sheaf of continuous functions, to the sheaf of continuous functions, one introduces the sheaves of meromorphic functions and the sheaf of meromorphic functions on any Riemann surfaces. On any Riemann surface, one introduces sheaves of holomorphic functions, sheaves sheaves O, it is denoted by O, sheaves O introduces a sheaf O of holomorphic functions and a sheaf M of meromorphic functions on any Riemann surface of meromorphic functions. On any Riemann surface. Any surface X. Yeah, I mean in the same way. So we just for any subset we consider for holomorphic for O we consider this holomorphic functions or meromorphic functions. So again, the restriction homomorphisms are obvious, and then the sheaf axioms are also obvious, since again the crucial fact is that for a function to be in holomorphic, it's a local property. So so the first sheaf axiom is satisfied because it's a function, and the second sheaf property is satisfied because for a function to be holomorphic is local. Yes, and yeah, again for meromorphic, yeah, the same. And okay, and then a bit different definition, but very important, is the following. So if X is a Riemann surface, then we can define O star, so X Riemann surface, U open set. Then we can define O star of U. The vector space, the space of the set of everywhere non-zero, holomorphic functions, non-zero holomorphic functions f u in or maybe it was not so good to say it in this way, the set of holomorphic functions from u to c star, c without zero. Um, and with the operation with the group structure defined by multiplication, with the group structure given by multiplication. Yes. So we consider everywhere non-zero holomorphic functions. Yeah, well, with the group structure given by multiplication. Yeah, and then okay, and then the restriction homomorphisms are again obvious. Yeah, yeah. The restriction homomorphisms again are obvious. And then again, this is a sheaf. Then O star is a sheaf. Yeah, and the proof is the same as for just usual holomorphic functions. Okay, then this is all for the lecture.